Good afternoon, students. Let's start solving today the problem of the root locus. The problem is draw a root locus for a given system and then comment on the stability of the system. So you have to draw a root locus and then you have to comment on the stability of the system. The system is given by g of s, h of s is equal to k whole divided by k divided by just a minute. K divided by s into s plus 3 into s plus 5. So you have to comment on the stability of the system and then you have to plot the root locus. Okay. So it is very simple. So let me start with the stepwise procedure for this. Okay. So in step 1, you're going to identify the number of poles and you're going to identify the number of zeros and you're going to identify the number of branches. So remember this. Now, how do you identify the number of poles here? So the number of poles can be identified from this particular characteristic equation. Okay, this particular characteristic equation. So the characteristic equation is s into s plus 3 into s plus 5. S into s plus 3 into s plus 5. So the number of poles will be 3. Okay, the number of zeros will be 0. And how do you identify the number of branches? The number of branches will be if p is greater than z. If p is greater than z, then the number of branches will be equal to p. That is, n will be equal to 3. Okay. Now, which are the poles? So you just find out the roots of this characteristic equation. There are 3 roots: 0, minus 3, and minus 5. So these are the 3 poles. We say that these are the 3 poles. Then after this, you have to identify the number of zeros. That means these are the value of s actually which makes the transfer function infinity. Okay. Then you should also find out the value of s, that is zeros. So there are no terms in the numerator. That means the value of s making the transfer function 0 are called as zeros. So you already know that. So here you don't have any numerator term, so hence it is 0. You don't have any roots there. So it is z is equal to 0. Hence, since p is greater than z, so we consider the number of branches is equal to number of poles. So here these are the starting points also. Remember, root locus will always start from a pole and it will end at 0. Now, what are the ending points? What are the ending points? The ending points are infinity, infinity, and infinity. Because there are no zeros, the root locus will approach towards infinity. The root locus will approach towards infinity. So always the root locus will start from a pole and then it will end at 0. If there are no zeros, then root locus will directly approach towards infinity. So you have to remember this, and also the characteristic equation is you have to find out the roots of the characteristic equation. Always the roots of the characteristic equation will give you the number of poles. The roots of the characteristic equation will always give you the number of poles. Just a minute. the roots of the characteristic equation will always give you the number of poles. So please remember that. So this is the step 1. So you have to identify the number of poles, you have to identify the number of zeros, you have to identify the number of branches. Okay. So this is step 1. So next, coming to step 2. Step 2 will be section of real axis. We call it as section of real axis. So this you have to do a pole zero plot. It is a simple plot, of course. So I'll just do it here. So it's a pole zero plot. Means you have to just take the real axis, negative real axis, because you have the poles lying to left half of S plane. So you take the negative real axis and you have to consider it. Okay. So just take the negative real axis and you plot the poles. Is it clear? So you have to start plotting the poles. So these are the poles. One pole is at 0. The other pole, it is at -3. And one more pole, it is at -5. Now here you take the sections. The first section is between 0 and -3. The second section is between -3 and -5. Then after -5 is the third section. So if I take a section here like this, so how do you say that? How do you say that this section is under root locus region? So if the number of poles and number of zeros, if you add it and if you get it as an odd number, then you say that this region is of root locus region. Now, if I take the section here towards the right side of this, if I add the poles and zeros, it is 1. So it is a root locus region. So I call this as root locus region. So if I take the section here to the right side of this, it is 2. Hence, this is non-root locus region. So if I take the section here, it is again a root locus region. Okay. So it's again a root locus region. So you have to take the sections and then you have to start doing like this. Okay. So these are the section of real axis. And also, so very importantly, you can also predict a breakaway points. Okay. So the breakaway points will exist whenever there are two adjacent poles, and between that, if it is a root locus region. Okay. You can see here, there are two adjacent poles, that is 0 and -3. Between that is the root locus region, and hence there is a breakaway point here. So one breakaway point you can expect here. Then between -3 and -5, anyway, those are the two adjacent poles, but you don't have any breakaway points since it is a non-root locus region. Then after -5, it is a root locus region, but you don't have any adjacent poles, hence you cannot predict any breakaway points. Okay. So according to the general predictions, we have got one breakaway point, but there is a procedure to find out where exactly this breakaway point will lie. So that we will see. Okay. Next step. Step 2. So step 1 is over. Okay. Step 2 is over. Next, we will go to the step 3. So under step 3, we have to find out what are angle of asymptotes. Something called as angle of asymptotes. Okay. So what are angle of asymptotes? Angle of asymptotes are nothing but the angles which shows the path of the root locus approaching towards the infinity. So asymptotes will always show you the path through which the root locus will approach towards infinity. So you have to find out this angle. It is given by 2q plus 1 into 180 degree by p minus z, where this q will be from 0, 1, 2 till you can take up till p minus z. Okay. Now you have to start calculating now. P is 3, Z is 0. So you will get 0, 1, 2. You have to just substitute 0, 1 and 2. So theta 1 becomes equal to 60 degrees and theta 2 becomes equal to 180 degree, and theta 3 becomes equal to 300 degree. Okay, so you just substitute 0, 1, 2 respectively to this Q. So you are going to get 60 degree, 180 degree and 300 degree. So you have also found out the angle of asymptotes now. Is it clear? So once you have found out the angle of asymptotes, then we will start finding the centroid. So we know what are the angle of asymptotes. Now we will find out something called as centroid. So centroid is a point. So I'll rub this. Centroid is a point at which the angle of asymptotes will meet. So you have to find out in step 4 as centroid. So how do you find out the centroid? Centroid is given by sigma is equal to summation of real part of poles, okay, minus of summation of real part of zeros divided by p minus z. So this is the formula that you are going to use. Summation of real part of poles minus summation of real part of zeros divided by p minus z. Now what are the real parts of poles here? It is 0, minus 5, minus 3, minus 5. And there are no zeros here. So you can take it as 0. And if you divide it by 3, so you are going to get approximately minus 2.66. So these are the poles. That is, these are the centroid from which from the real part of the poles you have found out. Okay, so this is the centroid. So this will be the step 4. So once you have done that, then we will go on to step 5. So we'll move on to the step 5. So under the step 5, you have finding the breakaway point. You have to find out the breakaway point. So breakaway point is a point from which the root locus will break into the branches. Okay, the root locus will break into branches. So for that, you have to find out the characteristic equation. So the characteristic equation is 1 plus g of s h of s is equal to 0. So from this you will get 1 plus g. What is g of s h of s? It is s into s plus 3 into s plus 5 is equal to 0. Okay. So from this you are going to get the cubic equation. Remember. So cubic equation you are going to get. So it is s cube plus 8 s square plus 15s plus k is equal to 0. So you have got this cubic equation. So once you have got this cubic equation, you just arrange for k. That is, you have to arrange k is equal to f of s, some function of s. That means k, you take it as minus s cube, shift all the terms to the right hand side. So minus s cube minus 8s square minus 15s. So take this and now you take dk by ds, that is k, differentiate k with respect to s. You are going to get 3s square plus 16s plus 15 is equal to 0. So if you solve it, so you are going to get one root as minus 1.21 and the second root as minus 4.11. So please verify this. You are going to get these two roots. Now you see, so this minus 1.21 I have plotted, if you remember. So this was the pole 0 plot. It was 0, minus 3 and minus 5. So between 0 and minus 3 was the root locus region. So minus 1.21, it lies between 0 and minus 3 and hence it is a valid breakaway point. Okay. We call that as valid breakaway point. Now, minus 4.11, it lies between minus 3 and minus 5, which is a non-root locus region, and hence this is a not valid breakaway point. It's a non-valid breakaway point. It is not valid. Okay. So this is also one method, or the other method is you can always find out the value of k. Substitute back this s value to the k and find out what is k value. So if I substitute minus 1.21, so you're going to get the positive value of k as plus 10.28. So if since you're getting the value of k as positive, so you can also say that it is a valid breakaway point. So if you substitute minus 4.11, the k value becomes negative, and hence again it will not be a valid breakaway point. Okay. So this is, since k value is positive, it will be a valid breakaway point. Is it clear? So these are the this is the step 5 where I can find out the breakaway point. Okay. Next is next uh, step is step 6, right? Step 6 is intersection with imaginary axis. So we will take this intersection with imaginary axis. Okay. So you have to find out where the root locus is intersecting the imaginary axis. So to find out that, you have to construct a roots array. So for that, you require a characteristic equation. You start from the characteristic equation, that is s cube plus 8s square plus 15s plus k is equal to 0. So from this, you construct a roots array. So roots array to be constructed like this. So it is s cube, s square, s power 1 and s power 0. You write it in the descending order. Then what are the coefficients of these s terms? You write all the coefficients of these s terms. It is 1 and one more is 15. The other is 8 and one more is k. So you can see for s cube, the coefficient is 1. For s, it is coefficient is 15. You have to consider the odd powers of s. You have to consider the odd powers of s. Then you have to consider the even powers of s. So here I have considered the odd power. So 1, it is starting with s cube. So 1 and then 15, then 8 and k. Now, how will you get this number? So to get this number, it is simple. 8 into 15 minus 1 into k. 8 into 15 minus 1 into k divided by 8. So you have to get the number like this. So the number will be 120 minus k by 8. And this is 0. Similarly, you have to also find out the number here. So for that, you consider these two. 8 and 120 minus k by 8. So for that, it will be again 120 minus k by 8. This entire term multiplied by k into 0 into 8. Anyway, that is 0 divided by 120 minus k by 8. So finally, you're going to get it as k. Okay. So this is how you fill the roots array. Now here, you have to identify the row of zeros. Row of zeros in the sense, the value of k which makes the row as row of zeros. So that is called as marginal value of k. So you can consider this 120 minus k by 8 is equal to 0. So if I substitute k marginal value as 120, then this becomes the row of zeros. So this becomes a row of zeros. So the row which is above the row of zeros is the row from which we have to construct the auxiliary equation. So from the auxiliary equation only, you are going to get this actually the intersection. Okay, so this is the row of 0. You should not consider this k. You should not directly equate it to 0, because if I equate this k to 0, then this becomes unstable. The entire system becomes unstable. So you should not consider the row as s power 0. The row which is above the s power 0th row should be considered as the row of zeros, from which you have to construct the you have to get the marginal value of k. So k marginal value is 120. So above this, now let me construct the equation. It is 8 s square plus k is equal to 0. So 8 s square plus 120 is equal to 0. So s will be equal to approximately plus or minus 3.8j. Okay, 3.8j. That means plus 3.8 below the above the imaginary axis from the origin. it intersects at plus 3.8 units, and below it intersects at minus 3.8 units. Okay, so this is the intersection with imaginary axis. So since you don't have any complex poles, so you will not have any angle of departure or angle of arrival. Actually, next step 7 will be that you have to find out the angle of departure or angle of arrival in case if you have the complex conjugate poles. That we will see in the upcoming problems. But right now you don't have any angle of departure, so you need not find out this. Since you don't have any complex conjugate poles, you need not find out this angle of departure. Okay. So let me quickly plot this now. Keeping all this data, now I have to plot the root locus. Okay. Let me plot the root locus. So for that, you please leave some one or two lines from the graph, and then you draw this y-axis, then let the x-axis be like this, and on this you consider 2 centimeters as 1 unit. So you can always consider 2 centimeter as 1 unit, and then you can plot it. So here will be 0, approximately here it is minus 3 and minus 5. So I have marked the poles exactly to the scale. You have to do this. Okay. So once you have marked these poles, then you can mark the breakaway point and the centroid. So the breakaway point is here, which is at minus 1.21. Okay. Then you have the centroid here. This is the centroid. Approximately it is at how much? Minus 2.66. So you have the centroid here. So mark this breakaway point and centroid. From the centroid, you draw a line at an angle of 60 degrees, which will be the angle of asymptotes. So this will be the angle of asymptotes. So this is one line, and this is already it is there. So at 180, I will not consider. So already the line is there. So you can just write it. This is theta 1 is 60 degree, and theta 2 here it is 180 degree, and theta 3 is 300 degrees. So you can construct this. So once you have constructed this, now you have to draw. You have to mark the intersection with imaginary axis. So this is the 3 units. 3 units you have to take up on the imaginary axis, and then you have to mark it. Okay. So this is 3 units, above 3 units and below 3 units. So just I'll mark this. Okay. So this is how much? This is plus 3.8 J, and here it is minus 3.8 J. So you can consider that, and above which you can write the marginal value of K, which is K marginal value is 120, and here it is marginal value is 120. So K marginal value is 120 here, and here also K marginal value is 120. Above this point, actually the system becomes oscillatory in nature. So it means that. Okay. Now the thing is, you have to draw a root locus. Now how to draw the root locus is the question. So we will quickly draw the root locus. Now the root locus will always start from a point, and it will always start from a pole, and then it will end at 0. We already know this. So it will start from this 0, and it comes to this breakaway point. Okay. Now here also there is a pole, correct? And now it comes to this particular breakaway point. It cannot go towards left hand side because it is a non-root locus region. Remember, it will not go here. So it comes to this breakaway point, and from the breakaway point, you can see here, this is the angle of asymptotes. That means this is actually showing you the path of infinity, correct? So these are the plots which is actually showing the path of infinity. So you have to plot it now in such a way that your locus will approach towards infinity. So this is the freehand sketch. So you have to plot like this. So this is a point, and you already know where it is intersecting with imaginary axis. So this will be infinity. So this is infinity. This is also an infinity. And from -5 also, there will be plot, a straight plot, which is approaching towards infinity. So there are three branches, as we said. There are three branches since P was greater than Z, N was equal to P. So if you remember, there were three branches. So three branches also it is approaching towards infinity since you don't have any zeros. Okay. So here you can say about the comment on the stability of the system. So if K is between 0 and 120, so absolutely it is stable, no problem. So if it is K is 120, then it is marginally stable, correct? So the system is marginally stable, and if K is greater than 120, then system becomes unstable. Okay, the system becomes unstable. So you have to make this comment also on the plot, and you have to give this plot. Okay, so I have done it very approximately. So please follow it in the graph sheet and produce this root locus. Okay, thank you very much.